we're going to start with our very friendly Italian Antonio. He's going to talk to us about some things that aren't maybe remote execution compatible that could be made remote execution / remote cache compatible. The title of the talk is "Will it remote execute?" So yeah, I'm looking forward to hear about that. Antonio.
Nice to meet you, everyone. Welcome to this meetup. So the title of the meetup has already been revealed. It's "Will it remotely execute?" It's not all about execution. It's just going to be a bit of caching because I couldn't quite figure out how to make everything run remotely. And just a few words about me. So my name is Antonio Di Stefano. I'm a DevX engineer at EngFlow. We try to make builds faster, and sometimes we succeed. I love collecting rubber ducks. In fact, I have one with me right now. So if you want to talk about rubber ducks, come to me after. No complaints will be allowed. And I love hacking around build systems and build tooling. I'm infamous apparently for writing Snake on Bazel. And that's all people remember, sadly, about me. So please don't do that. So what is remote execution and why does it matter? So remote execution is this protocol that you, especially Ola, are very familiar with, that allows you to run lots of things in parallel over a distributed system and cache them if you already run them once. It's extensively used by Bazel, and often the reason why people migrate to Bazel is that they can run things remotely in such a distributed fashion and make things exponentially faster than they would be locally. And this talk is about how to integrate things with remote execution. How do we create interesting remote execution clients? And sometimes even outside of build systems themselves, which we partially do. But let's start with the simpler case, how Bazel integrates with remote execution, and why it's the simplest, because there are some constraints that remote execution has that are already part of Bazel. And so let's look at how remote execution works in the simple client implementation. The full disclaimer: this code is not supposed to compile. Don't try. I'm not fond of slideware. It's just trying to explain what we want to do with remote execution. And so the first thing we do is we check what the remote execution server can and cannot do. In this case, we only have caching or execution. If either of them is available, then let's try to use remote execution. The thing we do right after is we get a command, and this command is pretty much what you imagine a command to be. So it's a list of strings that run on a system, have inputs, and can generate outputs, and have an environment defined in which they run. And so we generate an action from it, and we check if that has already been run in the past, and if there is a cache entry on what is called the action cache. If there is, we might want to download the outputs, which depends. Some implementations do, some not, depending on certain flags you might have enabled or not. But if not, then we try to run this, and there is two scenarios here. We can run it remotely, so the server has remote execution capabilities. And the first thing we try to do is we try to see what blobs do we still need to upload on this remote execution system. We start with the ones gathered from the inputs of the command, then the command itself and the action itself. We also do need to upload those products because the protocol always refers to the digest of these things. And we upload each of the missing ones. And the next stage is, of course, we try to execute it. And if it's successful, usually the remote execution system will cache it itself. So we don't need to be explicit about that. And if successful, again, we try, if needed, to download the files. There's also the case where we're running this locally. And if the execution is successful, we can also update ourselves the action cache, even when we're running things locally. And we may have to upload certain outputs. This is oversimplified. It's much harder when you actually try to implement it than this. But at a very abstract level, this is what Bazel does. There is a variant of this protocol where, like, you can actually try execution before trying to find the missing blobs. And I like to call this optimistic remote execution. So you're hoping that the inputs are already there. The advantage there is that you may already have everything remotely. So running would be faster because you don't need to upload much else, and you just run the execution. If I'm not mistaken, this is what, for example, Goma does, which makes sense in such a large code base as Chromium, right? You have lots of contributors. The code base is huge. Really, like the files that a single developer can change compared to the rest of the size of the code base are a trivial amount. So you may just want to execute things first. And so there's just these two variants. They're very similar, but overall, there is nothing too complex going on. But there are some invariants in here that become visible rather quickly. So in order to do this first step of finding the missing blobs and really even defining the action itself, you need to have pre-declared all the inputs and the outputs for an action, right? And this is not an invariant that most build systems have, right? Bazel has it, Vector has it, some have it, but not every build system has it. Think about Make and Ninja. They don't necessarily enforce this invariant, and so you may end up trying to run an action remote execution without all its inputs, and in that case, it will fail. Or even worse, you may check the action cache without all the inputs, and may end up getting wrong action hits, right? Cache hits. So in some cases, these invariants are really hard to enforce. And in the past few months, we've been trying to bring remote execution to CMake. We've partnered with this company called TP. And what they do is really interesting. They basically created a build system on top of CMake that tries to fix all the things that CMake doesn't do out of the box for you, and also do some additional nice things. And with CMake, you really have the same constraints you'd have with Ninja Make, because it doesn't build things itself. It's going to invoke another build system down the road. And really, with CMake, you can distinguish two kinds of action, right? You have compilation and linking, which we can solve really easily on remote execution, and then you have everything else. For compilation and linking, we really need a tool that is able to look at a command, and after looking at that command, is able to figure out, these are all the inputs of this command, these are all the outputs, and then by doing so, by inferring inputs and outputs, you eventually have the same invariants that Bazel has out of the box. And there are three major clients that do this. We have Goma, Reclient, and RECC. We decided to go for Goma because when we started doing this, Reclient was not open source yet, and we didn't really have much experience with RECC, whereas we have plenty of experience with Goma. And so we just decided to go for that. And so this is how Goma works. So you invoke Goma CC, which acts like a compiler wrapper. So you basically prepend the compiler invocation with Goma CC. So Goma CC, whatever the flags, the input files, and the output file. Then this sends a command to a component called compiler proxy, which is a daemon that you run locally, and you infer all the inputs and outputs. Once you have this, you can just start the usual workflow of sending the command, trying to check the action cache, and so on that we've just explained with Bazel. Except this uses these optimistic implementations that's going to try to run the command first. And then if it fails, it's going to either try to upload the files, or in some cases, even try to run it locally as a fallback. And then there's the last step, which is everything went fine. But then the real problem here is, how do we run everything else? So we've been working a lot on the LLVM code base because it's a really good example of a really solid, hard to work with CMake code base. It takes a while to compile. I know some of you are shaking your head, like I see PTSD everywhere in this room, and I'm really sorry. And infamously, LLVM built some tools during its build that then it uses to generate more code. And we can't quite easily run this on remote execution because those tools are ad hoc tools, and we'd have to write an implementation to discover dependencies for each of them. So we tried to be a bit smart about it, and we developed a dual-layer remote execution, where the second layer is the remote execution you're all familiar with, and that's used for compilation and linking. But the first layer, is it that pizza for me? No, so it's not for me. But the first layer of remote execution is just a single instance remote execution that does not run at the high level of granularity that we're used to with Bazel, but rather it runs the whole build. So it's almost a catch-all remote execution. And rather than scaling horizontally on that single instance, we scale vertically. So we're going to assign a big instance in there that runs the whole build, but then we can parallelize much better when it comes to compilation and linking, which anyway is most of CMake builds anyway. And so we have a little demo of building an LLVM. Now, some of you would enjoy it, looking at the numbers that we get. So this is the local build. We start with the local build. And it does take a while. This is sped up by a lot. And we get all the way down to linking, where we inevitably fail because we don't have enough resources on this instance. So we're left crying 18 minutes later because we really can't build it. So we try just running with no parallelism at all, because at least in this case, we're going to have enough resources. And once again, we split this up because it takes almost as much. And half an hour later, we finally build the LLVM. So that takes a while. Right? That's not the kind of build we want to see now. Let's try it with remote execution. So in this case, we also merge configuration phase and build phase with TP. So there is actually more going on in this build than there is in the other one. Yeah, you can already see it's much faster. Let's skip a bit, and in 3.5 minutes, you get the same build. And so this is the power of having this dual-stage remote execution, really. It almost has the same benefits of a build without the bytes in Bazel, if you're familiar with it.
Is the 30-minute number you gave just a minute ago the combination of failed build and the successful one? Or did the second one take 30 minutes because it was only on a single core?
Yes, it is. So like basically there's 30 minutes where like they were not two separate builds. So the second part was just a continuation of the failed build.
I see.
So it was not a retry from the beginning. And that's why we summed them up.
I see.
Could probably make it a bit faster, but it's still going to be longer than 20 minutes. So,
all right, sure. Because when you did it the second time, there's a bunch of cached objects I already used.
As well. Yeah. So like it's really just starting from linking in the second phase. And so by doing so, we get benefits of remote execution even where we normally wouldn't have it. And because we're also parallelizing inside remote execution, all the compilation and linking, really there is a lot of free available resources on that single remote execution instance we have as the first layer. It also allows us to have multiple stages of caching.
Dual layer approach, when you have like a single step where it builds custom targets, doesn't handle situations where you first build a custom target and then use it to build another custom target and then use it to do something like multi-step custom targets.
So does it handle building multi-step targets? Yes, it does, because at the end of the day, this is just like any other instance running CMake itself. So the first stage is just running a CMake build. And so it can also run nested builds and so on as well. 2 minutes. All right, we're going to speed run this last one. So the last one is the most interesting one, but I'm going to have to talk really fast because it's really complicated. So let's talk about Webpack, which is, by the way, a work in progress. I've not finished this one quite yet. There are some problems. If you notice them, please don't say it. So Webpack is not even a build system. I mean, it is a build system, but it pretends not to be. It's a bundler for JavaScript. So it takes a big file with lots of dependencies, merges it together in a single file, right? It takes a whole project to a single JavaScript file. It can be extended through loaders, which are this API in JavaScript that allows you to take a file that is not JavaScript and turn it into JavaScript with optional source maps. And a loader is just a function that eventually calls a callback with the generated code. But there are some problems with this approach. So outputs are strings and objects. They're not files. There are no shell commands involved, just opaque functions. So how do we cache that in a protocol that works around commands? And inputs are declared during execution. As you can see, the example in this case is this to that dependency. So if the two phases are mixed, it's really hard to have dependencies upfront. So the first problem, outputs are strings and not files. And we can just, because the number of outputs is limited, it's bound, we can just statically map them to a file. So we usually have these two objects, out, which is a string, and is the source code generated. We just map it to a file with always the same name, and then there is source map, which is a JSON object. We just serialize it as a JSON. and we just create files out of it. Second problem, no short commands, but rather opaque functions. So what do we do about that? We have a protocol that works around commands, pseudo commands. So we transform functions into an equivalent command. In this case, this loader, which is magicloader.js, with the function loader, takes some files as a configuration. We transform it into this equivalent command. Because at the end of the day, we really don't care if we forget about running it remotely and we just want to cache it. This is enough. It doesn't have to run. It doesn't have to be a working command. It needs to look like a command. That is the important part. Problem number 3, inputs are declared during execution. So what we can do here is that we can either take the approach of reclient and rec of inferring commands, but then we would need to execute that function because it's opaque. And that would basically mean running the whole loader. So we split it into dependency gather and loader execution. And we can cache these two parts separately. This is the bit that is not complete just yet. Like dependency gathering as it is right now can actually cause some serious problems. So this is the bit that I've yet to figure out. But if you split them into two parts, then you can also cache them separately and basically act like Goma and reclient do. And that's it. Any questions? And do I have time for questions?
One question.
All right, one question. Thank you, really kind Unnar.
Any questions?
Hola.
The Webpack, is it a good candidate though for remote caching? Because usually things that are very fast and just bundle stuff up are not.
I mean, it's fast until you involve TypeScript, I think. So the loaders can be arbitrarily slow. Right? They're just transformations of any kind. The bundler itself is not slow. That's why I focused on just the. It's not really slow. That's why I just focused on the loaders themselves. But loaders can be arbitrarily slow, and I've seen multiple cases of complex TypeScript sources that they take a really long time to be transformed.
Thank you.